All right, Chapter 8, Section 2. Hopefully by now you've got a good idea of how these Markov chain things work. This section is going to open your eyes to a much easier process of being able to do these problems than even Section 1. If you thought Section 1 was easy, well, that's good. But this section will be even easier, which is the good news. So let's just remind you real quick what we were doing back in Section 8.1. Section 8.1, we started with our example using a tree diagram. We're going to do that again here just to make some connections. But real quick, after we do our tree diagram, I'll show you kind of what it means and what ultimately we can do instead, a much shorter way of doing the problem than making a tree diagram. Of course, involving a matrix. And you'll see that coming up. Tree diagrams are great, but they work best when you have small problems like the example we did in 8.1, which was only a 2-stage problem. But you wouldn't want to make a tree diagram if you're going to do 10 stages, right? That would be way too many branches, really hard to keep up. So there's got to be a better way, and there is, and it involves using matrices. So remember, back in 8.1, we talked about, the example we used was employed and unemployed. We labeled employed with 1, unemployed with 2. So when we made our matrix, and I talked about the A11 spot being, first row, first column. Well, in the matrix, it referred to, because it was 1 and 1, it referred to being employed, because employed was represented with a 1, to employed back to employed. So being employed this week and then being employed next week, and that probability would go there. The A12 spot was the probability of being employed and then going to unemployed, because 2 represented unemployed. The A21 spot was unemployed to employed, and the A22 spot was unemployed and then unemployed again. So we're going to obviously do that again when we make our matrices this time. But if we wanted to note, for example, how many stages, you're kind of going to see it like this. So what this means right here is this would mean going from employed to unemployed on the 3rd observation, like 3 weeks from now. So this is asking, hey, what's the probability that you're employed this week and will be unemployed in 3 weeks from now, after 3 stages? So if I ever write, P11, 5, what this means is you're starting employed. I want to know what's the probability you'll be employed 5 weeks from now. And if I change this to 10, it's the probability of being employed 10 weeks from now. If I make this 2 and 1, move this back to 5 or whatever, this is being unemployed now to what's the probability that you'll be employed 5 weeks from now. So that's kind of the idea. Sort of this number in parentheses just kind of denotes how many stages we're talking about in our problem. So the transition for a 2-state Markov chain here, this is, I don't know if it's the same one that we looked at in section 8.1. It might be. But we're going to use tree diagrams real quick to find the 2-step transition matrix. So basically just after 2 stages. Let me go back in my notes real quick. Okay. It's weird because the textbook says 3rd observation, but 3rd observation is actually the 2nd stage. So it's really weird how it numbers these things. But anyway, so let's say we have to make 2 tree diagrams for this real quick, because we have to pretend, we're starting from being employed. We'll make that tree diagram. I'll actually move it over here a little bit. Get on this leaf here. Being employed to employed, unemployed, that's 1 stage. And then being employed or unemployed after the 2nd stage. And I'll fill those values in a second. The second tree diagram is if we start unemployed, us going to employed, unemployed, and then employed, unemployed after 2 stages. So let's fill out these numbers. So remember, employed is meaning the first one. Unemployed will be the second. So this right here is a 1-1 spot. So that's employed to employed. So if I'm employed and I go to employed, it's 0.8. Employed to employed is 0.8. The 1-2 spot means employed to unemployed. So employed to unemployed, that 0.2 would be this branch here. Then right here, this is the 2-1 spot. So that would be unemployed to employed. So unemployed to employed, that'd be this branch right here, which would be 0.6. Oh, we already did employed to unemployed. That was 0.2, remember? And then lastly, the 2-2 spot is unemployed to unemployed, which is this last branch here. So that's 0.4. So that's just filling in those numbers that were given to me in that matrix up here. Let's go ahead and put the same numbers in for the second side of this. So unemployed to employed is 0.6. Unemployed to unemployed is 0.4. Employed to employed is 0.8. Employed to unemployed is 0.2. Unemployed to employed is 0.6. And unemployed to unemployed is 0.4. So just to fulfill this all out, right, the top branch here, you'd multiply these 0.8 plus 0.8 or 0.8 times 0.8 together to get 0.64. Unemployed, this branch here, employed to unemployed, would be 0.16. Again, just multiplying 0.8 times 0.2. Multiplying this branch together, or these branches together, 0.2 and 0.6 makes 0.12. And then finally, 0.2 times 0.4 makes 0.08. And we'll go ahead and fill this one out as well. This will be multiplying these branches, 0.48. This one would be 0.12. 0.4 times 0.6 makes 0.24. And 0.4 times 0.4 makes 0.16. So we're familiar with tree diagrams. We're familiar with how they're laid out. We're familiar with how to get those values, multiplying the branches together. But now what's interesting is, let me go up here real quick. Let's make the matrix after 2 stages. So after 2 stages, what's my probability of being employed to employed? So employed to start and then employed to finish. So that's the 0.64 plus the 0.12. So adding those together makes 0.76. All right, the 1-2 spot here is employed to unemployed. So employed to unemployed is 0.16 plus 0.08, which makes 0.24. All right, I'm getting to something. Don't worry. I know I'm taking my time, but I am going to make a really good point here coming up soon. This spot here, the 2-1 spot, that's unemployed to employed. So we're starting unemployed. That's this tree diagram to employed. So that results in 0.48 plus 0.24, which makes 0.72. And then lastly, this last spot, the 2-2 spot, is unemployed to unemployed. So unemployed, we started with, and we ended unemployed. So 0.12 and 0.16 added together makes 0.28. So that's 0.28. Now this matrix that I just made, this is the matrix that represents the likelihood of being going from employed to employed after 2 stages, employed to unemployed after 2 stages, unemployed to employed after 2 stages, and unemployed to unemployed after 2 stages. Now, why that's significant and why this matrix is important is because there's actually a connection. There's a pattern that we just sort of discovered, but I'm just going to go and outright tell you what it is because I don't really know how to show it to you too well without just kind of being like blatantly obvious. What that matrix is it is the matrix we started with squared. Boom. And it's to the second power because the exponent is representing how many stages or how many stages we're going through. So we were talking about after 2 stages. So that's why you would square it. If I want to know after 3 stages, I would take it to the 3rd power. Bam. All right. So what happens here is just really, really convenient. Because if I want to know a certain outcome after a certain number of stages, all I have to do is take my OG matrix, whatever it was, the 0.8, 0.2, 0.6, 0.4. Oh, went too far back. The 0.8, 0.6, 0.2, 0.4. If I remember, if I did that correctly, I don't know if I just did that correctly or not. No, I got those wrong. It's 0.2, then 0.6. But anyway. And just raising it to the power of whatever number of steps I'm looking for. So if I want to find after 6 stages or 6 steps, it'd go to the 6th power. And this is as easy as just typing it in the calculator, which is very, very nice. So let's just try this quick shortcut on the example 1 that we just did. Let's see that it works. We had 0.8, 0.2, 0.6, and 0.4. Let's raise it to the 2nd power, meaning after 2 stages. Let's type it in our calculator and let's see what we get. So I'm going to delete that, but it's all good. So let me clear this off. Let's go to our matrix menu. So remember, 2nd, this button here takes us to the matrix. I'm going to put this matrix in. It's a 2x2 matrix. 0.8 times, what is it? Not times, 0.2, 0.6, and 0.4. Okay, so there's my matrix. It's matrix A. Let me just double check that I put everything in there, right? 0.8, 0.2, 0.6, 0.4. Okay, let's go out of here. Oops, wrong button. Let's select that matrix that we just created, matrix A, and let's raise it to the 2nd power. And we'll look what we got, 0.76, 0.24, 0.72, and 0.28. These are the exact same numbers. Well, I erased it, but if you rewind this video like 3 minutes ago, those are the exact same numbers we got when we made our tree diagram and put everything together. So it works. It's a very, very useful shortcut, just being able to take your matrix and raise it to the whatever power you want it to. So let's try just doing that real quick on some of these. So here's a matrix already made for us. Let's find the 2-step transition. Matrix P2, this just means after 2 stages. So all we're going to do is type this matrix in our calculator, raise it to the 2nd power. It's the 2nd power because it's asking us to use the 2nd power. And let's see what we get. Then we'll answer the question, if the system is initially observed in state 1, what's the probability that is in state 1 2 observations later? So we'll get to that momentarily, but let's go ahead and type this in the calculator. So go back to the calculator. Let's go back to our matrix menu. Let's edit this matrix. We're going to make it a 3x3 now. And we got 0.3, 0.3, 0.4, 0.5, 0.5, 0, 1, 0, 0. Let me just double check. That looks good. Because it's easy to type things in wrong. So, okay, everything looks like it's good. So let's get out of here. Let's take that matrix that I just, oops, wrong button. It's cool. Let's take that matrix that I just made and let's raise it to the 2nd power. And there's our result. So now let's look at the question we were asked here. The question in part 2 here is asking, if we started state 1, what's the probability that we're in state 1 again 2 observations later? So this is the 1, 1 spot, right? State 1 to state 1. So we're looking at the 1, 1 spot of our matrix. And that is 0.64, the very top left value. So hold on a second. Yeah. So basically what this part B is just asking you to do is just look at the matrix and pick a number out of it. If I asked for, what's the probability that we started state 1 and ended in state 3 instead of this, if we wrote state 3, then it would be the 1, 3 position on our matrix, which would be the 0.12 number in the top right. So that was just asking for a specific value, some random arbitrary one, but there it is. That's really all this math is. Let's talk about this real quick. Example 4, the transition diagram for a Markov chain is shown below. Find the matrix of three-step transition probabilities for the Markov chain. So we're just making a matrix. This is similar to what we did in 8.1. I've got 3 stages, so I know I have a 3x3 matrix. Let's start with the 1-1 spot. So starting in 1 and then going back to 1 is 1/4. So 1/4 goes up here. Then we have the 1-2 spot, which is starting in stage 1 and going to stage 2, which is a 3/4. All right, then we have the 1-3. So starting in 1 and going to 3. Now, if I start at 1, there is no arrow that goes to 3. So that must be a 0 there. All right, then this would be the 2-1 spot. So going from 2 to 1, notice there is no arrow going from 2 to 1, so that's a 0. 2-2, the 2-2 spot, notice there is no loop back upon itself on 2, so that's also 0. And then the last one is the 2-3 spot. So going from 2 to 3, you can see is 1. And then lastly, we're going to do 3-1. So going from 3 to 1 is 1/2. 3-2, there is no arrow going from 3 to 2, so that's 0. And then 3 back to 3 is 1/2. And so that's your matrix. Now you'll notice that all these rows add up to 1. 1/4 plus 3/4 is 1. 0 plus 0 plus 1 is 1. And 1/2 plus 1/2 is 1. That's not a coincidence. It's probability. Probability is supposed to add up to 1. And each row is representing its particular stage, from stage 1, from stage 2, and from stage 3. Or not stage, but losing the word here, but state. State 1, state 2, state 3. They all sound the same, man. Okay. All right, and this last example, example 5, this is real quick. So we're going back to the example 1 matrix, which is 0.8. Let me go back and find it. 0.8, 0.2, 0.6, and 0.4. And it's asking, find the probability that she will be... all right, so the consultant is unemployed this week. Find the probability she's unemployed 4 weeks from now. So we're going to take our matrix, raise it to the 4th power, since we're looking for 4th week. And whatever the matrix we get, we're looking for unemployed to unemployed. That's the 2-2 spot. So it'll be the bottom right. But let's go ahead. Let's type this in the calculator. And the answer to this question will be the bottom right value, since that's the 2-2 spot, meaning unemployed to unemployed position. So just quickly type this in. I shouldn't have deleted it, but I got to type it in again. We'll type it in again real quick. Doesn't take too long. I need a 2x2 matrix. 0.8, 0.2, 0.6, 0.4. Now let's take that matrix and let's raise it to the 4th power. So there's my values. I'm looking at the bottom right, since that's the 2-2 spot, which is 0.2512. So 0.2512. That's the probability. That answers this question, unemployed to unemployed. It's as easy as that. I'll see you guys in the next one. All right. Bye.